So we want to know how much protein there is. Like, for example, if you buy pet food, you know, pet food will have a certain number of grams of protein, grams of carbohydrates, that type of stuff. And there are different methods to determining how much protein you have in a particular sample. And so this is one of the methods. The method is based on converting all the protein nitrogen to ammonia and then determining the amount of ammonia by titration. So this ran into problems. I don't know if you heard about this or not, but there's, I think, some pet food company that was trying to boost its percent protein in their pet food. Did you hear about this? So they put melanin in there. Melanin is like plastic, and it's not made to be consumed, but it has nitrogen in it. And since the method wasn't determining how much protein, but the method was determining how much nitrogen, it artificially boosted the amount of protein in the food. But unfortunately, people didn't find out until a lot of pets have died. I don't know exactly how many pets died from that food, which was adulterated with melanin. But this is the same kind of thing. This is not really detecting how much protein. It's just saying, okay, if you detect this much nitrogen, then we can kind of correlate that with how much protein there is in the original sample, because protein does contain nitrogen. Not all proteins do, but some of the proteins. So I don't know if this is a proper...
What if it's concentrated? Or heated concentrated?
All right, so let's take a look. The method is based on converting all the nitrogen to ammonia and then determining the amount of ammonia by titration. The percent nitrogen in the sample under analysis can be calculated from the quantity of ammonia produced. Interestingly, the majority of protein molecules in living matter contain just 16% nitrogen. So they'll use this correlation. They'll determine how much nitrogen is in there, and then based on a percentage like this, they'll just estimate how much protein was in there. And so if they get 16 grams of nitrogen, then they can estimate that there was about 100 grams of protein in there. So we're just going to do a titration here. 1.843 gram sample of meat is heated with concentrated sulfuric acid. The sulfuric acid is there to digest the meat. And a catalyst to convert all the nitrogen in the meat to ammonium sulfate. Okay, so the first step is is they eat up the meat with sulfuric acid and convert all the nitrogen in there into ammonium sulfate. Then excess sodium hydroxide is added to the mixture. The excess sodium hydroxide is going to convert all the ammonium into ammonia. And then you heat it. You heat it to drive off the ammonia as a gas, because the ammonia likes to stay dissolved in water. It likes water. And so this is what I mentioned on some of you that had gas formation for ammonia. Ammonia is tough sometimes because it just sticks to the water. And so what you can do is heat it or shake it to drive off the ammonia, but it's not that effective. Heating is the most effective, actually. Heating it will drive off the ammonia. And so if they heat this long enough and hot enough, then all the ammonia will be driven off as gaseous ammonia. All the nitrogen from the sample is found in the ammonia. So what we can do is we can figure out how many moles of nitrogen that was, which is then absorbed in and neutralized by 50.00 milliliters of dilute sulfuric acid. So they're just going to titrate aqueous ammonia solution with sulfuric acid. The excess sulfuric acid requires 35.61 milliliters. Okay, so here, what are we doing here? The ammonia is then absorbed in and neutralized by dilute sulfuric acid. So this is kind of weird. So what they're doing is they're trying to isolate the ammonium. The ammonium sulfate is in this digestion mixture here. And so they're kind of going in circles here, but they're going in circles just so that they can they can isolate it from the rest of the stuff in there. So let's take a look at this. And so we can just kind of map it out, what's happening. So the protein contains nitrogen, about 16% nitrogen. Then the H2SO4 converts that into ammonium sulfate. And then the sodium hydroxide converts that into ammonia, AQ. And then the heat drives it off as ammonia gas. Plus other stuff. Okay, once we have the ammonia gas, this should be pure. And so this is all mixtures up until here, and then we get the pure ammonia gas. And this happens in like, I'm going to do this in 2 steps here. Then we take the ammonia gas and add water to that, and that's going to form ammonia aqueous. Okay, so this should be pure aqueous ammonia. And then we add sodium hydroxide. Are we adding sodium hydroxide? Let's see what we're adding here. All the nitrogen from the samples found in ammonia, which is then absorbed and neutralized by 50.00 milliliters of dilute sulfuric acid. So then we add some sulfuric acid to this, H2SO4. And they add 50.00 milliliters of dilute. Dilute is like 6 molar or less, H2SO4. Okay, and then they're going to neutralize this. This is going to be excess H2SO4 here. The excess H2SO4 requires, okay, and so what that's going to form is it's going to form ammonium sulfate again, plus leftover H2SO4. Okay, then what they're going to do is they're going to take this leftover H2SO4 solution and they're going to titrate it. The excess H2SO4 requires 35.61 milliliters of 0.4498 molar sodium hydroxide for its titration. I don't know if these numbers are the same as yours. 35.61 milliliters. Of 0.4498 molar sodium hydroxide. To neutralize. A separate 25.00 milliliter sample of the dilute H2SO4 requires 22.06 milliliters of 0.4498 molar sodium hydroxide for its titration. All right, so this is quite a tedious problem. How many people have done this? Nobody? Kiana, how much time did you spend on this one? I'm sorry? You haven't solved it yet? It's kind of a tedious problem. They should have given you a little bit more information. So, I don't think probably nobody's solved it. Let me see how much time people have spent. This is spending too much time on this particular problem. What's that?
You can see how long we spent on a problem.
Yeah, this one I hadn't done because this was normally I have a list of problems that I like to do, but this one the problems I'd like to do were missing, so I substituted this problem. I thought this was going to be a more straightforward titration, but we can figure it out. I mean, what we have to do is we have to do 2 titrations, basically. Doing 1 titration is usually enough, but we'll do 2 titrations. One, we want to figure out, this says dilute. Dilute is very qualitative, so we want to know what is the molarity of this. What is the molarity of that? And so in this separate analysis, we're taking 25 milliliters. So we can figure out the molarity by just doing a titration calculation here. So let's go ahead and do the titration calculation here. The molarity of the dilute H2SO4, this is the stock solution, is just equal to the moles of H2SO4 divided by the liters of H2SO4 solution. So the moles of H2SO4 we're going to get from stoichiometry. And since the titration required 22.06 milliliters of sodium hydroxide, what it says 22.06 milliliters of, actually, did I get that right? Let me just see. Sodium hydroxide, I mislabeled it. Should be sodium hydroxide. For its titration, we'll just do this. 22.06 milliliters. Actually, I'll need some more room. So let me do it over here. This is the sodium hydroxide solution. Then we're going to convert it into liters. And then we're going to convert it into moles. And then we're going to use a mole ratio here. The mole ratio is going to come from the balanced chemical equation. H2SO4 requires 2 moles of sodium hydroxide for every 1 mole of H2SO4. And this is going to form sodium sulfate and water. 2 waters in this case. This is 2 to 1 mole ratio, so 1 mole of H2SO4 requires 2 moles of sodium hydroxide. And then we divide this by how many milliliters. We had 25.00 milliliters of H2SO4 solution, and then convert that to liters. And this should give us our molarity of the stock solution. The 22.06. I'm going to get rid of this. Times 22.06. Actually, let me use my calculator. I forgot my calculator. 22.06 times 0.4498 divided by 2 divided by 25. 0.1984. We're allowed 4 sig figs here. And so I'm going to carry an extra digit, the 5. And this will be the molarity of the H2SO4 stock solution. So 0.19845. So we added here 0.19845 molar. So we could figure out how many moles of sulfuric acid we added here. And so how many moles of acid did we add? Well, we just take the volume times the molarity. So I'm going to write that in here. Let's go with a different color. So this will be my next calculation. So I'll just do 0.05 times 0.19845. Point 0.0099225 moles of H2SO4. This is 9.9 millimoles. People who do a lot of titrations like to use millimoles sometimes. So if we move the decimal 3 over, that gives us 9.9225 millimoles worth of H2SO4. Now, did
How different is like a chemist doing actual research for a journal? How different is that process of titration from our process? Like
it's just the same, basically?
Really?
Yeah.
That's crazy.
Yeah, I did a lot of titrations.
I figured it'd be more.
No, I use the burettes and that kind of stuff,
Like
pipettes and
published
stuff.
research.
But there are different ways you do titrations. I did different kinds of titrations. So, for example, I titrated like how much sodium ion was present. It wasn't acid or base, but it's essentially the same process. This is volumetric. This volumetric stuff's been around for over a century. People are still doing.
Can you get pretty precise?
You can, yeah. It's pretty precise. Can be. So when we added all the stock solution here, did it all react? And the answer is no, it didn't all react. They said it's an excess of H2SO4. If it's an excess of H2SO4, what we need to find out is how much H2SO4 reacted. Because if we figure out how many moles of this H2SO4, this excess H2SO4 we added, actually reacted with the ammonia, then it's simple. It's a 2-to-1 mole ratio of ammonia we need 2 moles of ammonia for every mole of H2SO4. And then we could figure out how many moles of ammonia, and once we figure out how many moles of ammonia, we could figure out how many moles of nitrogen we had. And once we get the moles of nitrogen, then we can figure out how many grams of nitrogen, and then we can use the percent by mass to figure out how many grams of protein there was in the original. And so this is a bit of a pain, because if we just did the titration here, we'd be done. You know, if we did a careful titration here to figure out how much ammonia we generated, then this is over. But instead, what we did was we added way too much here, and then did another titration at the end. And so that's where this second titration comes in. The second titration comes in with the leftover H2SO4. So based on the leftover H2SO4, here we're not going to want to calculate the molarity of the leftover H2SO4 because it's all mixed up. You're adding 50 milliliters to however much you had there in the first place, and we don't know how much we had in the first place. So since it's all mixed up, all we're going to do is we're going to use this titration to figure out how many moles of H2SO4 we have at the end. And so this is why I'm going to moles and not molarity. I want to figure out how many moles I'm using, because it doesn't matter the volume of the liquid. The volume of the liquid could go up or down, but it's not going to change the number of moles inside. This is why when we're doing titrations, it doesn't matter if you squirt more water into your Erlenmeyer flask, because it's not going to change the number of moles inside the Erlenmeyer flask. That's fixed, but the volume will change the concentration. But that's all right if it changes the concentration. And so all we do is we do another calculation to figure out how many moles of H2SO4 are left unreacted. That's the leftover H2SO4 here. And so this would be the next calculation here that I'm going to do down here. And so this case, I don't want the concentration. I know I use 35.61 milliliters. Of sodium hydroxide solution. We convert that to liters. And then we use the molarity. This is called the sodium hydroxide standard solution. Standard solution, we have a well-known concentration, whereas the H2SO4, we call that a stock solution because we don't have the concentration so precisely known. 0.4498 molar. And then it's a 1:2 ratio, 1 mole of H2SO4 over 2 moles of sodium hydroxide. And then we'll stop here because that's what we want to calculate. And so I get, I'm just going to do 0.03561 times 0.4498 divided by 2. 0.008008 moles of H2SO4 left over. And then what we're going to do is we're going to calculate the moles of H2SO4 consumed or used. This is consumed by the ammonia. And so if we start off with 9.92 millimoles and we end up with 8.00 millimoles or 0.01 millimoles, how much did we use? And so we just subtract the two. So I'm going to take 0.0099225 minus 0.00808. Actually, I'm allowed 4 sig figs, so I need to go 008 6. I'll carry 5. And so I ended up using 0.00191381, if I did this correctly. Looks like it is. So if I know how much of the H2SO4 reacted, then I'm just going to say it's going to react with 2 moles of sodium hydroxide for every 1 mole. And so I'll just continue the calculation, 1 mole of H2SO4. Sorry, not sodium hydroxide. Now that H2SO4 didn't react with sodium hydroxide, it reacted with ammonia. Reacted with the ammonia. And so what am I trying to calculate? Let's see what I'm trying to calculate here. What is the percent protein in the meat? All right, so then I'm just going to continue this. 1 mole of nitrogen for every 1 mole of ammonia, and then 14.01 grams of nitrogen for every 1 mole of nitrogen, and then times 100 grams of protein per 16 grams of nitrogen. This is going to give me the grams of protein. So times 2 times 14.01 times 100 divided by 16. 0.3351. Titrations we typically have 4 sig figs. I'm going to carry 1 extra. I'm not allowed 5 sig figs, but I'll carry it. Anyway. Yeah. So now I know how many grams of protein there are, and then I need to find out what the total mass is to get the percentage. So looking up the total mass here, 1.843 gram sample of meat. This seems low. The percent protein is the grams of protein over the grams of meat. So 0.33515 grams of protein over 1.843. Total times 100. %. That's 5. So I get 18.19% protein. This number seems too small. If it's meat, it seems too small. So maybe I made an error. So what I would do is I'd go back and check, if I made an error somewhere. But this is basically how you'd figure it out. It's kind of a convoluted titration. They could have gotten the titration done in fewer steps. But since you already spent time, I'll leave it on there. It's just one question out of all of them. Or maybe I'll just delete it. Or just make it extra credit. I may just do that. Just make it extra credit. Okay. Any other questions? So we're doing experiment 5 today. We're not trying to figure out the percent protein. We're trying to figure out the percent KClO3 in an unknown solid. And so what we want to do is we want to determine the percent KClO3 in a mixture. We have to know a little bit more about this mixture. So this is the mixture here. It's just a white powder containing potassium. What's KClO3 called? Potassium chlorate. And so it's a white powder. And this white powder contains solid KClO3 plus other stuff. Now the other stuff is going to be inert. Inert in this context just means unreactive. And so there's some other white solids in there that are inert. It could be just one other, or it could be multiple. And so what we want to do is we want to just isolate the KClO3. In fact, we just want to react the KClO3. And so let's take a look at the chemical properties of KClO3 first. Thinking about the chemical properties of KClO3, is KClO3 very reactive in metathesis reactions? Metathesis reactions, we think, so we look at potassium ions. What does potassium ion precipitate with? It's group 1. Group 1 cation. What do group 1 cations precipitate with? How about what do group 1 and ammonium ions precipitate with? Nothing. And so totally unreactive in metathesis, potassium ions. How about acid base? Is potassium ion a good acid? Where is potassium ion on the acid chart? Well, it's not on the chart. It's not on the chart, meaning they just ran out of room, or it's not on the chart because it's not an acid. Bronsted acid. What do you think? Huh? It's not an acid. So metathesis, nothing. Acid base, nothing. How about redox? Yeah, potassium ion is on the redox chart, but it's extremely strong or extremely weak. It's number 2. It's number 2, the second weakest or the second strongest? Not the strongest. It's the weakest. It's the second weakest oxidizer on the chart. What is the weakest oxidizer on the chart? Lithium ion. And therefore, it's not really reactive here. So I'll just draw an X here. Potassiums. How about chlorate? Does chlorate have any metathesis? No. Chlorates, acetates, and nitrates are all soluble. They don't form gases either. Acid-base, chlorates are the conjugate base of a strong acid. The conjugate base of a strong acid, those bases are so weak, they're not really even considered a base. It's like chloride. Chlorate's like chloride. How about redox? Is chlorate on our redox chart? No, it's not. Chlorate's not on our redox chart. Does that mean it's unreactive? Or does that mean they just ran out of room? What do you think? Unreactive or run out of room? Well, probably to analyze this, we'll probably take a look at the oxidation states. And so let's look at the oxidation states of potassium chlorate. Which one goes first, potassium, chlorine, or oxygen? Potassium at +1. Alkali metals go first. And then oxygen or chlorine? Oxygen at -2. And that means chlorine must be plus what to add up to 0? So -2 times 6 is -2 times 3 is -6. +1 is -5, which means chlorine has to be +5. What charge does chlorine like to be? Now, chlorine doesn't really like to be +5. What does chlorine like to be? -1. -1 is the preferred charge of chlorine. +5 it's not as happy with. And so it's not on the redox chart because there's not enough room. Basically it's an oxidizer. And you would know it's a pretty good oxidizer. Well, it's all relative, you know, here. It's all relative because we need to know what these numbers mean. So this is the combination of theory. You know, we could use theory to calculate these numbers. Very simple theory to calculate these numbers, maybe oversimplified. But we have to put a meaning on those numbers. The meaning comes from observations. You know. And one of the observations is, you'll see, potassium chlorate is not so stable. And so it is an oxidizer. If it's an oxidizer, that means it's electron poor and it wants to oxidize something. And so if you have potassium chlorate, we need something for it to oxidize. But there's nothing for it to oxidize. You know, oxygen's happy at -2. Potassium has no more valence electrons it can give up. And so there's nothing for it to oxidize. This is like, you know, those zombie things. You know, the zombie needs fresh meat to eat. But, you know, if there are just other zombies around, there's nothing to eat. And so this would be the predator here. But the situation is okay, this. What we're going to do is we're going to heat this up. And when you heat things up, then you can force things to happen. And delta, this is the symbol for heat. So normally, this is an ionic lattice. We have potassium ions and chloride ions, you know, and they're in their positions in the lattice. So it goes potassium, chlorate, and we build up this lattice like that. And they stay in their positions. You know, at room temperature, there's going to be some vibrational motion, but otherwise they're staying in their position. You know, they could vibrate. They could vibrate like the ions could vibrate back and forth. Potassium ion, chloride ions, they can vibrate like this. But the chlorate ion itself can vibrate also. You know, when we look at chlorate, chlorine's in the center, and then we can have oxygens like this. So we could draw this with an octet on the oxygens, and that leaves a lone pair on the chlorine. The only problem with this particular structure are the kind of high formal charges. When we look at the formal charges here, each oxygen will have a negative formal charge, and the chlorine is going to be 1, 2, 3, 4, 5, plus 2. So it's kind of high. We can lower the formal charge by expanding its octet. And so what a lot of people do is they'll expand the chlorine octet by creating a double bond. If we make one double bond here, then the formal charge on chlorine drops from plus 2 to plus 1. Actually, this one has 0 formal charge. Let me erase that. Note the formal charge and the oxidation state are different. What's the oxidation state of chlorine? In each of these structures, the oxidation state of the chlorine is still plus 5. Yeah. I can draw 2 double bonds like this, and so some books will show it like this with 2 double bonds. If I were to draw 2 double bonds, that's going to drop the formal charge on chlorine to 0 and leave me with just 1 formal charge on this oxygen here. A negative charge there. But it doesn't matter which of these 3 structures I go with. All of them will have a plus 5 oxidation state on chlorine. Plus 5. Meaning it wants electrons. Whether it's got a 0 formal charge or a plus 2 formal charge, it wants electrons. We primarily use formal charge when we're looking at acid-base and Lewis structures. But when we do redox, we just primarily care about the oxidation state. So the reason I'm showing this structure is because at higher and higher temperatures, these start to vibrate. And when they start to vibrate, what happens is the bond is like a little spring, like this, and it vibrates. And so higher and higher the temperatures, the oxygen and the chlorine are going to be vibrating. Like that, the bonds themselves are going to be vibrating. And what can happen is, you know, because there's a distribution of kinetic energies, some of these are going to be vibrating quite violently, maybe. Maybe so violently that the chlorine and the oxygen can kind of collide, you know, in this vibration. Well, they're already colliding because they're bonding together, but collide more severely. And then, do you know what can happen? What can happen is, what's more electronegative, chlorine or oxygen? Oxygen's more electronegative. So oxygen, this is why we gave -2 to oxygen rather than -1 to chlorine. Oxygen is more electronegative, so oxygen is going to get its choice of electrons. But what can happen is if you have these violent vibrations, what can happen is that the chlorine wants to oxidize something, and it's going to like cannibalize itself. So this compound is going to eat itself because the chlorine is going to eat the electrons off the oxygen. So this is like if you're starving, you might as well just eat your leg. And so this is kind of what it does. The chlorine will take the electrons off the oxygen, and do you know what we're going to get? We're going to get potassium chloride and oxygen gas. When we look at the oxidation states here, potassium's +1, chlorine's +5, oxygen's -2. Over here, potassium doesn't change, but chlorine has changed. Now it's -1. So chlorine went from +5 to -1. How many electrons did it just gain? 6 electrons. We have 3 oxygens here. Each oxygen's -2, and the oxygen's going to go from -2 to 0. So we had 3 oxygens at -2, and then 3 halves times 2 is 3. 3 oxygens at 0. So that means each oxygen lost 2, and we have 3 of them. So 3 oxygens are going to lose 6 electrons total. And so this is self-cannibalized reaction here. We call this like an intra-compound redox reaction. This is only going to happen at, well, at high temperature, and it still happens slowly, this cannibalizing reaction, because oxygen wants the 2 electrons. And oxygen's stronger than chlorine, so oxygen should hold on to it. The only reason is because we're heating this up, and we can force this to occur. But even forcing this to occur, it's slow, so we have to add a catalyst. This reaction happens too slow, this self-cannibalizing reaction, because it doesn't want to self-cannibalize itself. And so the catalyst we're going to add is MnO2. MnO2 is manganese 4 oxide, or some people call it manganese dioxide. Geologists call this desert varnish because it forms a black coating on sandstones, a really pretty black coating on sandstones. And so the catalyst is there to speed it up. So KClO3 can undergo this type of reaction here. Let's take a look at this. This is from old exam 2. Which species is inherently unstable? So if we look at potassium permanganate, this seems to be unstable. Why? Not because of the potassium, not because of the oxygen, but because of the manganese. The manganese is +7, which means it's going to be quite reactive. This stuff should be very reactive. But it's not inherently unstable. Why isn't potassium permanganate inherently unstable? The reason is because, you know, there's no prey. This is a predator. And this predator can, of course, eat its own leg. But it's probably not going to do that, right? Unless you heat this up. Of course, if you heat this up, then maybe it could decompose, where it takes, you know, the manganese will take the electrons off the oxygen. But that's heating it up to a high temperature, so you want to be careful with this stuff. Otherwise, this is stable. This is stable because there's no prey. If you have like a room full of predators, then nobody has to worry about being eaten. Let's take a look at this one next. This one's ammonium nitrate. Now this one's a bit different because when we look at this, you know, hydrogen and oxygen, nothing unremarkable about that. That's +1, that's -2. But when we look at the nitrogen, the first nitrogen is -3. The second nitrogen is +5. As long as they stay apart, it's okay. So one is -3, which is on the rich end of the spectrum or the poor end of the spectrum. Nitrogen, what does nitrogen's charge vary from? -3 to +5. So one is on the rich end, the other is on the poor end. In fact, they're at the opposite extremes. So as long as they stay apart, there's no problem. And that's what they do. In an ammonium nitrate, you have ammonium, you have nitrate. But what happens if you start heating up ammonium nitrate? Then it starts to vibrate more and more violently, perhaps. And if you continue to heat it up, eventually you'll have the ammonium and the nitrate kind of collide. And when the two nitrogens come into contact with each other, there's going to be a tug of war for electrons. Who's going to win? Nitrogen versus nitrogen. Is it going to stay +5 and -3, or do you think they're going to come out with something else? Well, it turns out they're going to come out with something else. And so ammonium nitrate is inherently unstable. And the reason is you have an electron-rich cation and an electron-poor anion in the same compound. It's different than this, you know. We don't consider oxygen electron-rich. This for sure is electron-rich. And so ammonium nitrate is explosive. And like Lebanon, Beirut, Lebanon, that was a ammonium nitrate explosion that happened recently. And in China, there's a huge ammonium nitrate explosion there. Oklahoma City, ammonium nitrate explosion. So ammonium nitrate, we want to avoid heating this stuff up because if it can explode. Also, we want to avoid impacts because if you impact things, then the ammonium and nitrates can get closer together during that compression and cause explosion too. So some of these explosives are mechanically unstable. And so this is the reason is you have predator and prey in the same. You know, this is just predator unless you heat it up to very high temperatures. This is just predator, lithium perchlorate, there's no prey. CO2, this is just predator, but it's quite a weak predator, as we know from observations, from experience. So what we're going to do in this lab is this. We're going to decompose our potassium chlorate into oxygen gas and potassium chloride, and then we're going to capture the oxygen gas and determine how much oxygen. From the amount of oxygen, we can get the amount of potassium chlorate, and we can figure out what the percentage of potassium chlorate in our unknown must have been. And so there are two calcs that we're going to do for this. Let me try to save this before it crashes. I might be too late to save that. For Calc 1, what we're going to do is we're going to trap the oxygen gas, and then we're going to get the pressure of the oxygen, the volume of the oxygen, the temperature of the oxygen, and then calculate the moles of oxygen. From the moles of oxygen, we're going to calculate the moles of KClO3. From the moles of the KClO3, we'll calculate grams of KClO3. And then from the grams of KClO3, we'll calculate the percent KClO3 from calculation 1. The percent KClO3 from calculation 1 will just be the grams of KClO3 over the grams of unknown, the white unknown solid, times 100%. Calculation 2 is this. We're going to measure the mass of the inert plus KClO3, and then we're going to the mass of the reactants And then we're going to measure the mass of the products, which will be KCl plus the oxygen, but the oxygen escapes, and we're unable to measure its mass from the test tube. TT stands for test tube. Plus inert. The change in mass, delta mass, is equal to the mass of oxygen that escaped. And so let's say we have a half a gram difference. If there's a half a gram difference between the reactant and the product, so the half a gram is the oxygen that escaped because the KCl is stuck, and we'll be able to weigh it. And so from the delta mass, the change in mass, we get the mass of oxygen. From the mass of oxygen, we get the moles of oxygen. From the moles of oxygen, we'll get the moles of KClO3 using the equation. From the moles of KClO3, we'll get the grams of KClO3. And then from the grams of KClO3, we'll get the percent KClO3 in our mixture from calculation 2. And so we're going to calculate the percent two ways. Calculation 1 and calculation 2, hopefully they come out the same. They're supposed to come out exactly the same. If calculation 2, if this experiment just involved calculation 2, this experiment would be so fast and easy. We put in our KClO3 here. This is our KClO3. You're going to get an unknown sample from the stockroom. The unknown sample is going to contain a cork with the unknown number written on it. So I have unknown number 40. Make sure you write it in here. These weren't weighed out accurately. And so what you need to do is we're going to get another test tube like this. And we're going to tear it. When you tear the test tube, it says to use a piece of wire, but we don't have to use a piece of wire. The piece of wire is for these old test tubes. What we're going to do is we're going to just get a small beaker, put the test tube in here, and then just zero it. You can also weigh the empty test tube if you'd like. It might be safer to do that. What we need to know is we need to know how much unknown, how many grams of unknown we're going to put in here. So what you're going to do is you're going to just tap in the desired amount of unknown. They're probably going to give you more than the desired. Don't use all of it, what they give you, because if you use all of it, it might be too much. Our apparatus can only trap so much oxygen, and if you exceed the capacity of our apparatus, then you have to start the experiment over, because then we've lost track of how much oxygen we've generated. So tap in the desired amount of unknown. And then we need to add a little bit of catalyst. A little bit of catalyst is just the tip of the spatula. It's like a match head's worth, you know, from our tiny matches. So just put in a match head's worth in here. And so what we need to know is how many grams of white solid and how many grams of black solid we put in here. And so we got to weigh these things so that we can determine that. Okay, we probably should weigh the empty test tube as well. That way at the end we can figure everything out. All right, the next step here is we're going to mix the catalyst with our unknown sample and then set it up on our apparatus. The apparatus is going to look like this. Let me show you. This is experiment 5. So we want to mount this at about a 45-degree angle. We're going to use a utility clamp to do that. And so first I'll just place the utility clamp on here. There's a lock nut. This is the lock nut here, so I can loosen the lock nut. The lock nut jams against the back of this, and then you can rotate this to whatever angle you want. So I'm going to rotate this to about 45-degree angle and then lock the lock nut so it doesn't rotate anymore. And then I'm going to put my test tube in here. I'm going to clamp this at the very top of the test tube. There. Like this. And so that's the initial setup. Then I got to assemble the oxygen trap. We're going to trap the oxygen in this Florence flask here. And so the first thing, I'm just going to fill up this Florence flask with tap water. That's too much flow, wasting water. And then we're going to stick this stopper in here, this 2-hole stopper with one glass tube that goes to the bottom and another glass tube that terminates up there. And then I'm going to have an overflow beaker here. I'm going to fill this up about 2/3 with water, like this. And so the first thing I'm going to do is I want to purge all the air out of this line. We're going to have this line that goes from the tube from the bottom here. It's going to go up to this rubber tubing here, to this glass tube here. That's going to go in the beaker here. And what I want to do here is I'm going to capture the oxygen by water displacement. And so this tube is filled with air. That's okay. We're going to leave the air in there. And then as the oxygen gas is generated, it's going to add to the air already in here. And so as the oxygen gas is generated, it's going to push the air into the flask. As it pushes the air into the flask, then the water is going to go out this overflow tube into the beaker here. But what we want to do is we want to make sure that there's no air in this overflow tube. Because if there's air in the overflow tube, then we don't know how much water is being pushed out because we have all that air that comes out first before the water. And so what you're going to do is you're going to purge the air out of the overflow tube by either using a pipette bulb to force water in through the tube like this. Or in the lab manual, they say to cup your hand around the stopper and blow through this. And so essentially what we want to do is we want to make sure there's no air in the tube. So the way to do that I usually do, is just siphon water back and forth. So I'm going to siphon water back into the Florence flask. Do you see the water level rise in the Florence flask? Okay, then I can siphon water back into the beaker here. But I don't see any air bubbles here or here. You see that? And so that means I got rid of all the air out of there. All right, now what I want to do is I want to fill the Florence flask as high as possible so that I can capture as much oxygen. If I started the experiment down like this with a whole bunch of air in here, then there's not much room for oxygen, you know, if this is already filled with air. And so I'm just going to fill this with water by backfilling. So backfill, I'll just reverse the siphon. You know, this is just taking advantage of different pressures. Here, I'm going to backfill it just below the stopper. I need to see the water level inside the neck of the flask. And then when I do that, I'm going to seal this here tightly. Okay, now this overflow tube is filled with water and there's air trapped in here, but I can still siphon. Do you see I can still siphon water back and forth? Do you see the yeah. And what I'm doing here is as I'm siphoning water into the flask, it's compressing the air. If I siphon water out of the flask, it's creating a vacuum, low pressure. And so what I want to do there is this. I want the oxygen that I want to generate to add to the air in there. When I add, I'm adding the volume. So I want the volume of the oxygen plus the volume of the air to be additive. In order for the volumes to add up, that's Avogadro's law. In order for Avogadro's law to work, what has to be constant? The pressure has to be constant. And so what I need to do is I need to do a process called equalizing the pressure. So I have pressure of the air trapped in here, and then I have atmospheric pressure out here. Atmospheric pressure is pushing on the beaker. So what I'm going to do is I'm going to make the two equal. If I'm like this, then the pressure of the air trapped is higher than the pressure of the atmosphere. If I'm like this, then the pressure of the atmosphere is higher than the pressure of the air trapped. So what I'm going to do is I'm going to equalize the two levels like that. Once I get the two levels equalized, then I'm going to pinch the hose. They say to use a clamp, but I'm just going to pinch it with my fingers like this, and then I'm going to discard this. Now I know that the air trapped in here is the same pressure as the air outside. And then I'm going to replace the hose like this. Okay, so now I'm ready to go. I equalize the air pressure trapped in here. Okay, the next step is to get this stuff to decompose. That is to get the chlorine to oxidize the oxygen in there. And the way we're going to do that is we're just going to heat it. Now you want a hot flame, so you should get a nice cone on the flame. But we don't want to heat the hot part first, so we're going to gently heat this first. I have no catalyst in here. I'm not really going to decompose this. I'm just going to show you. You heat it softly first. Potassium chlorate has a low melting point. You'll see it melt. Once it melts and starts to bubble, then you can start heating it more vigorously with the cone part. The tip of the cone is the hottest part. And so heat it gently at first, and then start heating it vigorously once it slows down. Okay, as that's happening, oxygen gas is being generated, and the oxygen gas is going to be forced through this tube into the flask, and it's going to push the water level down. So I'm going to mimic that by just blowing in here a little bit. So after a while of cooking this, you'll generate some oxygen gas there that adds to the air. All right, so I'm cooking this. When should I stop? When you should stop is after like 5 minutes, nothing's happening, then you're probably okay. Just make sure it's all decomposed. Now we have air and oxygen gas trapped in here. But I want to make sure that the volumes are additive. In order for the volumes to be additive, the pressure must be constant. And so what I'm going to do is I'm going to equalize it. So I can force water back into the flask, or I can force water out of the flask. What I need to do is I got to make sure that this is the correct volume of oxygen at the correct pressure. And so I'm going to equalize the pressure like this by getting the two levels equal. Now the flask is higher. Once I get the two water levels equal, then I'm going to pinch the hose and then take the hose out of there, and this should be the volume of oxygen at the pressure generated. Okay, then once I get the volume of the water, I'm going to use one of those big grad cylinders over there to measure the volume of this. And that's going to give me the volume of wet, what we call wet oxygen gas. So this is from Calc 1. We're going to get the volume of wet oxygen. It's wet because it's been saturated with water vapor, you know, when you bubble it through the water or put it on top of the water. So the volume of the wet oxygen. What else do I need? I need the temperature of the wet oxygen. So I'll disassemble this apparatus here and then just measure the temperature of the gas with the thermometer back over there. What else do I need? I need the pressure of the wet oxygen. The pressure of the wet oxygen, this is equal to the atmospheric pressure because remember we equalize all the pressures. And to measure the atmospheric pressure, we're going to use a barometer. I think our barometer is broken over there. But let me see if Chem 164 let me just show you. The barometer is going to have a glass tube in the center filled with mercury. And then on here, we're going to have the millimeter of mercury. And over here, we're going to have the inches of mercury. And so we're going to read the right-hand scale. So let's say we're at 757, and then the next one is 758. And then we look at the meniscus. The meniscus for mercury is convex, like this. This is over-exaggerated. And then we look at the top of the meniscus. We read mercury from the very top. And then we estimate it. What is the height? It looks like it's 757 point X millimeters of mercury. The X, this is the estimated digit. But we have something that's more precise than estimating that digit. We have something called a vernier scale that's built into the barometer. And so we don't have to estimate this. Rather, we're going to use the vernier scale to read the 0.x millimeters. So the vernier scale, the way that's going, it's just a little metal plate that slides on the barometer. You can move it up or down. And so all we do is we, oh shoot. All we do is we slide this plate up or down until the bottom of the plate lines up with the top of the meniscus here. And so this would be the 757 here. And then this would be 758. And then on the vernier, there are going to be markings here on the vernier scale. 10 markings. And then all we do is find out which line up with the line on the right. And so most of these lines are going to be offset. So this first line's offset, second line. All of them except for one. Only one of these will line up. And the rest will be offset. And so I look at this and I look, okay, that's 5, 6, 7, 8. It looks like the 8th line lines up with one on the right, because all the other lines are offset. And since the 8th one lines up, then the reading here is going to be 757.8 millimeters of mercury. So we don't have to guesstimate it. It's just right off the vernier scale here. Zeros at the bottom, that would be 1. And the vernier scale just slides up and up or down. Like this one has a knob, you can raise it up and down, so this one's more expensive. In the Chem 4 we just have a little knob here that you have to manually slide this thing up and down to line it up. All right, any questions on reading the barometer? So hopefully we can do that in Chem 164. We'll see. But at the very least, take a look at that barometer over there. Okay, then we have the data for the experiment. Oh, the final thing is we need to reweigh the product with the test tube. Actually, we need to know how much the test tube weighs for that. And then once you're done, you can wash out the product. I think there's a waste container there maybe, or whichever. Okay, any questions? You can work in groups of 1, 2, or 3 for this lab. You'll need to check out the equipment from the stock room. I'll stop now.